We talked for 2 lectures about mostly historical stuff, which is important to know because this is this shows that things can be done, but they're not too easy. So now we are going to go to CFTs, and in CFTs we are very comfortable with CFTs. So the level of the discussion will change. So we will not be explaining so much some maybe mathematically difficult looking but unfamiliar things, but just how in the framework that we know and love, conformal field theory, how we can do things that we want to do. And what do we want to do? We would like to show that just starting from Euclidean CFT axioms, we can do Lorentzian physics, we can recover Weidmann axioms. So it's nice because Weidmann axioms don't come as an extra assumptions. They kind of they turn out to be built in these Euclidean CFT axioms. And we have done it only up to 4-point function level, so that's what I'm going to discuss today. And the strategy should hopefully be clear based on the first 2 lectures. So we are going to start from Euclidean CFT endpoint functions. And in order to define Weidmann functions from them, we have to go back from Euclidean to Minkowski. So we are going to take our correlation functions. First of all, we have to continue them to the forward tube analytically from Euclidean space. And then if we can check that this analytic continuation satisfies power law bound, then by using this very robust Vladimir's theorem, we will show that the boundary value is a distribution. And it's with a little bit of extra work, you can show that it satisfies all Weidmann axioms. And what it means, so what kind of power law bound you should aim for, we will start from a Schwinger function, which is a function of n-1 y's, but now we are going to take this y's. In Euclidean, they start with real values of times, and now we are going to complexify the times. So we're going to replace epsilons by epsilon plus it, where t is the real time. And now we would like to take the limit that epsilon goes to 0 to recover Minkowski physics. And before we take the limit, this function has to be analytic, and it has to satisfy the bound of this form. So this limit as epsilon goes to 0, it should not grow faster than 1 over epsilon to some power. And it should also not grow faster as some power of the distance between points, absolute value of y. So this looks kind of very natural and almost you can believe that if we get analytic continuation, we will probably be able to get such a power law bound, because in CFTs everything is power law. So we will just follow our nose, and this power law will come out of somewhere. So that's the goal, and we will. Of course, it's this power law bound, and the consequence that it's a distribution is going to be important in some regions of, for some causal orderings. For example, if there are light-like separations or multiple light-like separations, then of course we will only be able to show that our Weidmann function is a distribution. For some causal orderings, we will actually be able to show more. We will be able to show that the Weidmann function is an actual real analytic function, and I'm going to talk also about that. And for some other causal orderings, even though there are no light-like separations, still our analysis will give only the modest conclusion that it's a distribution. So an open problem will be for the future is to understand whether actually some stronger result can be shown, and perhaps in some of the regions where for the moment we only consider it's a distribution, actually it's a function. But what I'm going to talk here is kind of the first step in that direction. Okay, and this strategy that I described in the case of the CFT 2 and 3-point functions, it's basically obvious that it's going to work. Because 2 and 3-point functions, they have in CFTs explicit expressions. So this analytic continuation to the forward tube that we have to do, it's basically immediate. You just take, for example, a 2-point function in the CFT, which is just some power law. We replace times by complexified times, epsilon plus IT squared. And now, okay, so we get some expression which now depends on the complexified time, and you just have to check that this expression doesn't vanish as long as epsilon stays positive. So this is a little computation. You have to see, well, okay, can this expression vanish? For it to vanish, both real and imaginary part has to vanish. Can this happen? Then you see that in the forward tube, this doesn't happen. So that's kind of a trivial exercise. I'm not going to describe it here, but you can do it very easily, as you can imagine. And moreover, not only does this thing not vanish, but you can also easily show that it is bounded from below in absolute value by some function of epsilon. That's again just some trivial exercise in inequalities that anyone can do. And hence, this analytic continuation that we described is going to satisfy the power law bound. And so by this sequence of trivial exercises with 2 and 3-point functions, we are done. There is nothing else to be done. That's the end of the story. So you see, this approach is so robust. So for the 2 and 3-point functions, it works just immediately. And so we can hope that in the case of 4-point functions, with a little bit of more work, we will be able to accomplish something similar. So I really hope that it should be really obvious that for the 2 and 3-point functions, this is very easy. So, but if someone is doubting about, since I'm not giving any details, we have to discuss.
I don't doubt, but I think one question I have is, let's think about the 3-point function.
Yeah.
And you can put 2 points at 0 and 1.
Yeah.
And let's take the third point to the common light cone, the intersection of the light cones. Does it have a worse singularity than just crossing a single light cone? Like, what is the singularity? I guess I can just stare at the expression and look at it, but is it somehow worse when the third point approaches the intersection of the 2 light cones?
So for the case of 3 points, we'll just have to take a product of 3 expressions like that.
Mm-hmm.
So it's important that if all epsilons, which are the Euclidean time separations, if they are positive, if they are strictly positive, there is no singularity.
Right.
So it is of some interest to figure out what is the power of the singularity when you take the epsilons to 0.
Right. Mm-hmm.
So this power of singularity will certainly depend on it will depend on deltas in some way. And eventually it will enter into this exponent an here, because I've taken the maximum of 1 over epsilon k and an. So I do not have it on the top of my head, and indeed this power of singularity, it may depend on whether you're approaching a single light cone or whether you're approaching a double light cone. It will certainly depend.
Yeah.
I'm sure that on the double light cone, this power of singularity is going to be larger.
Mm-hmm.
And so this means that even though, you can do this analysis, and the conclusion of this analysis is that the the Whiteman function is a distribution everywhere, but it is a more singular distribution near the double light cone than it is near the single light cone. So you can kind of locally characterize the singularity of the distribution, and on the double light cone, it is a more singular distribution. Yeah.
Okay, yeah, that makes sense. Thanks.
But you know, for this kind of zeroth order analysis, you just know that there is some exponent, so there is some distribution. End of the story. In the zeroth approximation, that's it. And okay, so what else can be said about here is that in this case, just because we are dealing with some explicit expressions, the Whiteman functions are going to be ordinary functions everywhere except on the light cones. So in this case, there is no subtlety. So unlike we will see in the 4-point function case, this is, we don't know if it's the case, but at least for the 2 and 3-point functions, it's just like, you know, if you're on the light cone, there is some singularity and you have a distribution. If you are away from the light cone, it's an ordinary function, and maybe you will get some phases, but there is now, it's still a function. Nice and simple. Any other questions about 2 and 3-point functions? So basically what I'm saying is that, you know, all these classic papers which say that in the CFT, if you want to define Whiteman 2 and 3-point function, you just have to stick in I epsilon prescription. I'm just saying that that's true. There's no error here. So that's like indeed rigorously true. And it is very easy to show that it's rigorously true by using this Vladimirov theorem, which is good because we've been using these 2 and 3-point functions via epsilon prescription for a long time. So now let's go to the 4-point function case, and I'm going to just state certain facts about the Euclidean 4-point functions for identical scalars for simplicity. And so these are going to be, so I'm going to state some properties of 4-point functions that I'm sure that everyone or almost everyone is going to be very much familiar with.
Slava, before you do that, do you mind I ask a question? I'm a bit confused about the logic. So
yeah,
let me see if I understand the logic. So in we want to prove this reconstruction theorem to go from Euclidean to Whiteman axioms.
Yeah.
And in your original OS axioms, we had this power law bound in Euclidean, right? That was the first axiom.
Yeah.
And now the difficulty is that you want to prove also a similar power law bound as you approach the Minkowski signature, like as you continue Minkowski.
Yeah.
And generically for Osterwalder Schroeder, this was very difficult, and they had to appeal for this extra linear growth condition.
Yes.
But you in CFT, you're just going to do it directly on the 4-point function without invoking higher point functions.
Yes, I will be able to do it directly because of the extra control that we have in CFTs. For example, you will see I already did it directly for 2 and 3-point functions, while for OS, even at the level of 3-point functions, they would have to work already very, very hard.
But for 2, they can they do it easily? Like using
for 2, I think 2 I think is the only case when you can do it easily because it just has such a simple
like Alan Lemon representation.
Yeah, because you
Okay, thank you.
So yeah, exactly. So for the 4-point function, I'm just going to write down some properties of Euclidean 4-point functions, and I'm going to use these properties to cook up an analytic continuation. And I will just have to check all of this, you know, that it's analytic, that the linear growth, not linear growth, that power law bound is satisfied, and so on. So that's just you know, said like that, maybe you would think that at this point it's just bound to work, but there are a few things to check, so it's not totally trivial, as you will see. And in the Euclidean, you know, I'm just going to state some properties. You know, you can try to derive them from some more lofty axioms. In our papers, we do it. But here, you know, these properties, as you will see, they're just so familiar that I think everyone will agree, we are all sure that these properties are true, and in any axiomatic system, they have to be true. So the first property that I'm going to use is that if we are in the Euclidean, then the conformal block decomposition for the 4-point function, it has positive expansion, non-negative expansion coefficients, because I'm only dealing with unitary theories. And this conformal block decomposition converges in Euclidean space as long as the z variable is away from this cut from 1 to plus infinity, which is the usual S-channel Euclidean cut. That I think everyone agrees with that. And one way to see this property is that we can do a conformal transformation, which transforms from the z coordinate to the rho coordinate. And then the condition of z being away from the 1 infinity cut, it corresponds to the rho coordinate being in the unit disk. That's also well-known fact of Euclidean CFT. Any questions about that? Everyone comfortable? So another property I'm going to use is that the Euclidean conformal block in a unitary CFT, they can be expanded in the rho bar coordinates with some coefficients that depend in some way on delta and L. But the only thing that I'm going to use today is that the expansion coefficients here, they're non-negative, H and H bar are non-negative. And I'm also going to use that the difference of this H minus H bar, which is the eigenvalue of the rotation operator in the 0-1 plane, it has to be an integer number. H minus H bar is an integer. So this is again a property of conformal blocks, which is some special function. There are many ways to verify it. And finally, if I combine these two properties, the fact that the Euclidean correlation function can be expanded in conformal blocks and conformal blocks can be expanded in rho bar, I obtain a formula for, there is a formula for the Euclidean 4-point function with some positive expansion coefficients, P or H, H bar, non-negative, which are some combinations of the original conformal block expansion coefficients and the expansion coefficients of conformal blocks. And there are some powers, rho H, rho bar, H bar, and this expansion in the Euclidean converges as long as rho bar have absolute value less than 1. Okay. And the final property that I'm going to use is that in the Euclidean, if I stay in the Euclidean, and if I consider rho bar real, which means that I put my 4 operators on one line and at the points -1, -r, r1, then in such a configuration, the 4-point function is bounded by some power, by some constant divided by 1 minus r to the power 2 delta O, where O is the dimension of my operator. And this just follows from crossing, because in the limit when r goes to 1, I have these two pairs of operators getting close to each other, and these two pairs of operators getting close to each other. So I know the asymptotic of my 4-point function, this limit. It's actually, the asymptotic is 1 divided by this denominator. And so if it's 1 divided by the denominator, it's bounded everywhere by some constant divided by 1 minus divided by 1 minus r to the power 2 delta O. So these are basically all properties in the Euclidean that we will need.
Slava, are you considering all real delta, or are you considering like principal series to all of these statements?
I'm considering only real delta because I'm working in a unitary CFT, so all my deltas are supposed to satisfy unitarity bounds, and reality is one of the unitarity bounds.
Okay, thanks.
Actually, it would not work as easily for complex. Yeah. And okay, well, now I have to do analytic continuation. So, and how am I going to do analytic continuation? I'm just going to take this rho and rho bar, and I have to analytically continue them to the forward tube. So, and as long as in this analytic continuation, both rho and rho bar, so in the Euclidean, they were complex conjugate of each other. Now they're going to be some independent functions of x's in the forward tube. So as long as rho bar are less than 1 in absolute value, I can hope to get an analytic function. But there are a few things to check. So let's be a bit careful. Let's try to be systematic. So how do I perform this analytic continuation? So so the first thing is to analytically continue U and V. So I take U and V are given by some explicit formulas in terms of x's. So I assume that I'm in the forward tube. So the Euclidean times are ordered always, tau 1, tau 2, tau 3, tau 4. So since if I make now times complexified, then use U and V become some analytic functions in the forward tube. So they become analytic functions of x's. That's clear. And moreover, so these are finite analytic functions, and they are also non-zero analytic functions. So they are non-zero because, as we said, x squared never vanishes in the forward tube, because that was the property that we already used when we said that a two-point function could be analytically continued to the external tube. So 1 over x squared is never singular. So U and V are single-valued, non-vanishing analytic functions in the forward tube. That's easy. Everyone's happy? So now once we analytically continue U and V, we go to Z and Z bar. Z and Z bar, they are defined by these formulas in terms of U and V. So you can solve these equations. You get Z, Z bar equal by some square root formulas in terms of U and V. So U and V are analytic functions in the forward tube. So it means that Z and Z bar are at least locally analytic functions in the forward tube. Why locally? Because of the square root. So we have this forward tube, and somewhere in the forward tube there is this codimension 1 manifold, which I call big gamma, where the argument of the square root vanishes. So we have to think a little bit about what happens on this gamma. So away from the gamma, Z and Z bar are analytic functions, but what happens if you go around gamma? Rather, are Z and Z bar global analytic functions on the forward tube, or are they just local analytic functions? And if you go around, what can happen is that when you go around gamma, Z and Z bar are going to have some monodromy. They're going to be interchanged. The only thing which can happen is that they're going to be interchanged. So does this happen or not? You have to think a little bit about this. And what turns out to be true is that if you are in 2 dimensions, this does not happen. So in 2 dimensions, Z and Z bar are actually global analytic on the forward tube. And well, that's because actually in 2 dimensions, you can write explicit formulas for Z and Z bar. As you know, in 2 dimensions, you don't have to go, in order to define Z and Z bar, you don't have to go through U and V, but you can actually write explicit formulas like Z equals Z1 minus Z2, Z3 minus Z4, divided by Z1 minus Z3, Z2 minus Z4, and analogously for Z bar. So the existence of such explicit formulas, it shows that in fact Z and Z bar are global analytic on the forward tube. But in D larger than 2, there is no such, you cannot write a separate formula like this. The only way is to go through the square root formula. And actually, it turns out that in D larger than 2, Z and Z bar are not global analytic. So there is a monodromy. So you go around this gamma manifold and Z and Z bar get interchanged. So now you can get a bit worried because we would like to get a function which is global analytic, because that's the requirement to apply Vladimirov's theorem, but yes, Z and Z bar already not global analytic. So you may get a bit worried about what's going to happen. But as you will see, this monodromy is not going to be important because this in D larger than 2 dimensions, the powers that you are going to have here, rho to the h, rho bar to the h bar, they will always enter, in D larger than 2, there's always going to be, they will always enter symmetrically. So they're going to be always rho h bar plus rho bar times rho bar to the h. And so even though rho and rho bar have a monodromy, Z and Z bar have a monodromy around gamma, and rho bar hence also have a monodromy, but this monodromy is going to cancel once you stick in these local analytic functions into G. So it means that G is going to be actually single valued when you go around gamma, and single valued bounded functions which have potential singularities on codimension 1 surfaces. There is a removable singularity theorem which says that those singularities actually don't exist. So it means that G is actually going to be a global analytic function. So that's going to be fine. Okay, so I spoke for a while without interruption. Any questions so far?
Just to clarify, so why don't you also expect this combination in 2D?
Not in 2D, because in 2D you can have so there's a difference between 2D and 3 and higher D is that in 2D the transformation which exchanges rho and rho bar is a parity transformation which is not in the connected component of the conformal group. So you can actually have correlation functions where these terms don't enter symmetrically.
If there is no parity.
If there is no parity, yeah. And so if you want to analytically continue such a correlation function to the forward tube, it's very important that actually in 2D, rho and rho bar, Z and Z bar, rho bar are separately global analytic. So you don't have to deal with this monodromy. Mm-hmm. While in higher D, the transformation which exchanges rho and rho bar is a part of a rotation, so it's a part of the conformal group, and so these two terms are going to enter symmetrically, and that's very handy because in precisely in D larger than 2, they are not global analytic. So everything works out just as it should be, fortunately.
Thank you.
So Slava, you said that the block is an analytic function in the forward tube.
I didn't say that, but this is true.
I think did you really not say that? Okay.
Because I did not actually discuss blocks in the forward tube. I could, but we do it in our paper. But I said that block in the Euclidean allows this expansion in terms of rho bar, and then if I stick it into my 4-point function, I'll get an expansion for the 4-point function. And then I only work with that formula today. But you could also ask the question, what does the block do in the forward tube? And yeah, it's going to be an analytic function in the forward tube, global analytic.
Yeah, but would that not just be a consequence of it being a function of U and V? And you don't have to to define a block, you don't have to go through the row.
I am afraid you have to go, even for the block, you have to go to Yeah, you would. I'm afraid
can write it as
to
a
find the
series
block, you
expansion.
would have to go. So there, I'm not sure that the series expansions for the blocks in terms of U and V, such formulas exist, but I'm not sure they have a sufficiently large radius of convergence to allow you to define the block everywhere in the forward tube.
Yeah, so that's related to my second question. So is rho and rho bar, are they less than 1 in modulus?
So
the forward tube?
this is the most material part of our construction, to show that rho bar are everywhere less than 1 absolute value in the forward tube. That I'm coming to that.
Ah, okay.
That's the reason why everything works. If it didn't work, then it would be doomed.
Yeah, exactly. All right. Thanks.
But then, okay, what we do? Okay, Z and Z bar are local analytic, so we define rho and rho bar, which are again local analytic, and then we expand G as a power series in terms of rho and rho bar, like this. And now as I said already, as long as this series converges, which is going to be the case if rho bar less than 1. It's a series of analytic functions. So as I explained, monodromy around gamma is a removable singularity. There's no problem on gamma. So it's a series of convergent. It's a convergent series of analytic functions, and the convergence of analytic functions converges to an analytic function. So it's the sum of such a series is also an analytic function. So this basically proves that G can be analytically continued to the forward tube, provided that we manage to show that the rho bar is less than 1. And also, you see that we can bound every term in the series by its absolute value. And I'm assuming that there's going to be, I'm assuming this bound in Euclidean. And so this bound in the Euclidean, it extends to the bound in the forward tube, where now I have to put R being equal to the maximum of absolute value of rho, absolute value of rho bar. So now you see that not only do I have to show that rho bar is less than 1 in the forward tube, but I have to show that as you go to the boundary of the tube, which is the Minkowski space, this rho bar, they don't approach 1 too fast. And if I manage to show this, then I'm going to have a parallel bound and all the roses will blossom. So that's looks like a robust strategy. So, but for this to work, I have to show, as I said, I have to show that rho bar less than 1 in the forward tube. And moreover, I need a parallel bound on this quantity, 1 over maximum rho bar. How's it going? Everyone's with me? And, you know, for these facts, we have actually in our paper, we have 2 proofs. It's possible to prove these facts just by, you know, by manipulating the definition, the fact that Z is in some way related to U and V, and rho is related to Z, and so on. You can try to manipulate these simple expressions, and you can actually construct the proof that rho bar is less than 1 in the forward tube. It's elementary, but it's tricky. In fact, that's not the proof that we first found. This proof came late in the game, which shows that it's tricky. You can read this proof in the paper. You know, I'm not sure it's the best proof to present, so I'm not going to present it today, but I'm going to present another proof, which is actually total opposite of the first. It's not elementary, but I have a feeling that kind of explains what's going on, so in some intriguing way. So that I like this proof better, so I'd like to present this one. So this proof, it goes through a certain Cauchy-Schwarz-like inequality for this quantities rho and rho bar. So let me explain. So I'm going to take a point in the forward tube or a configuration in the forward tube, where in addition, I'm going to assume that that the Euclidean times of x1 and x2, they lie on one side of 0, and the Euclidean times of the other 2 points, they lie on the other side of 0. And if I have such a configuration, then I can define 2 other configurations, C12 and C34, which are reflection positive. Now, my reflection operation was defined, it's the Osterwalder-Schrader reflection, it was defined for Euclidean points. Now I'm going to extend this definition to points with complexified times. So if I have a complexified time, epsilon plus it, then this theta, it inverts the Euclidean part of the time, but it leaves the Minkowski time unchanged. It's like a natural generalization. And so the configuration C12 is defined by taking the points x1 and x2 and reflecting them, and C34 reflects the points x3 and x4. So now I have these 2 configurations, C12 and C34, which are also the forward tube, clearly, because the Euclidean times are ordered as they should. And now I'm going to state this Cauchy-Schwarz inequality for rho bar. So as I said, we are interested in this quantity, which I'm going to call R of C, which is the maximum value of absolute value of rho and absolute value of rho bar. So this is the quantity that we would like to control. And I claim that this quantity satisfies this inequality, so it's less than, so R of C is less than the square root of R of C12 times R of C34. So this is kind of it's clearly a very useful inequality to have, because this configuration C12 and C34, they because they only depend on 2 points, x1 and x2, and because they are reflection symmetric, you can show that their rho bar are real. And moreover, actually, you can derive an explicit formula for rho bar of this configuration C12 and C34. It's an easy computation because I mean, actually these configurations are kind of 2-dimensional in spirit, and since in 2 dimensions there are explicit formulas, you can imagine that for this configuration there are also explicit formulas for rho bar. And hence, if you are just given some configuration C, arbitrary configuration C in the forward tube, it's kind of hard to prove some inequality for rho bar of C, because in order to compute rho bar of C, you have to go through several steps, first U and V, then Z bar, then rho bar. I mean, it's like a mess. You cannot, it's hard to derive any inequality for rho bar of C. But it's very easy to derive an inequality for rho bar of C12 and C34 because they're reflection positive. And so basically, using the fact that this reflection operation, it doesn't actually, you take a point in the forward tube, you get the points which are again in the forward tube. This inequality, it allows you to quickly check that in the right-hand side, you get 2 numbers which are less than 1. And so the number in the left-hand side also has to be less than 1 in some controlled manner. So this inequality is really the key to proving that rho bar is less than 1, and also that you have a parallel bound, and actually get an explicit bound very easily. So the funny thing about this inequality is that we don't really have an elementary proof of this inequality. This inequality is, we guessed this inequality essentially, and then we constructed the proof. And the only proof we know for this inequality, well, we also checked it numerically and everything, is it goes through conformal blocks, which is really, I mean, I personally find that it's kind of intriguing, but it's also weird because rho and rho bar are more fundamental than conformal blocks. You know, conformal blocks are made out of rho and rho bar, but we are going to go the other way around. So the first thing to prove this inequality is to show that conformal blocks satisfy Cauchy-Schwarz inequality in the forward tube. So if you take a conformal block for some configuration C, then it's less than the square root of conformal blocks at configuration C12 and C34. So this, I'm sure that many people in the audience will agree that this is a plausible looking inequality, given what we know about the unitarity structure of conformal field theories and so on. You can give it a rigorous proof of it and so on, but you know, that's something that I'm sure many people will believe that something like that should be true. And then what you can do is that you take a inequality for a conformal block, and which is valid for any delta and del, and then you pass to a certain limit. Namely, you have to go to the delta going to infinity limit, stay in a twist of order 1. And then in this limit, conformal block behaves as rho to the delta, or rho bar to the delta, depending on what is larger. And so by passing to this limit, you derive this Cauchy-Schwarz inequality for rho and rho bar. So,
can I ask a question?
Yeah.
Have you already continued into region where the conformal block expansion already no longer converges?
Not yet, because it converges in the forward tube. It converges, and actually on the boundary on the Minkowski space it also converges in the sense of distributions. But here, you see, the funny thing about this proof that I'm presenting now for rho bar is that I'm not using any conformal block expansion. I'm just using conformal blocks as an auxiliary tool. There is no 4-point function here. Just take a conformal block as a special function.
Yeah,
it doesn't have to converge. The 4-point function doesn't have to converge because I'm just going to take one conformal block at a time.
Okay.
And this conformal block satisfies this inequality, I'm telling you.
Okay. To the extent that you're making a statement about analyticity property or of your 4-point function.
Not yet. I mean, not here.
Yet.
Here, I'm just taking one block. I'm only working with one block.
Okay, thank you.
4-point function involves many blocks, and you have to show that the sum converges. But here, just take one block, and take the Dolan-Osborne block.
Okay.
It's given by some explicit formulas in terms of 2f1s. I claim that if you take those formulas, analytically continue to the forward tube, then this inequality holds. That's the first.
Forward tube can be characterized by having rho and rho bar absolute value less than 1. Is that correct?
And I'm saying that if you know this inequality, then you can show that rho bar have to stay less than 1.
Okay, thanks.
Slava, I have a follow-up question.
Yeah.
So what about in, let's say, odd dimensions where we don't have a closed form of the conformal blocks? Do we need to again use a rho bar expansion of the conformal block and then go to the forward tube?
No, fortunately not, because you can. First of all, the 3-dimensional forward tube is contained in the 4-dimensional forward tube, so you can always work with 4-dimensional blocks for that case. That's fine. What you could be worried about is that whether, if, for example, I want to consider this problem in 5 or 6 dimensions, then I would have to repeat my exercise with 5-dimensional blocks, 6-dimensional blocks, and so on. But fortunately not, because I'm only proving the theorem about configurations of 4 points. And you can always do a linear transformation, putting these 4 points in a 4-dimensional subspace. And so then you are only allowed to work with 4-dimensional blocks.
Okay, I see. Thank you.
So the proof is correct, but it's a weird proof because, I mean, I'm just proving some geometric inequalities about some geometrically defined functions rho and rho bar. Why does it have to go through the conformal blocks? That's just kind of weird. And nevertheless, that's the only proof that, well, not the only proof, as I said, there are other proofs which are elementary, but it would be nice to, let's say for the Cauchy-Schwarz inequality for rho bar, that's the only proof that we have. So if somebody manages to come up with an elementary proof of this inequality, that would be a satisfying simplification of our story. Okay, so what do we know at this point? At this point, I explained basically how to show that the 4-point function, the Weidmann function of a CFT, 4-point function of a CFT, is a tempered distribution. That just follows from the arguments that I presented. And it's tempered distribution everywhere for all possible causal orderings, for all possible light cone singularities, double light cone singularities, and so on. But now I would like, in the second part of the lecture, I would like to go a little bit in specifics and say, okay, yeah, sure, but this was very general. But suppose that I don't want to know like a general result about a general 4-point function everywhere. I want to know some specific result about my 4-point function somewhere. I'm interested in some particular causal ordering. What are you supposed to do? So that's what I would like to discuss. What are you supposed to do in practice? Unless there are any questions. So in practice, you're supposed to do the following thing. You want to know, suppose that you want to know a Weidmann function at some 4-point configuration x1, x2, x3, x4. And in particular, you would like to know whether the Weidmann function there is an ordinary function or perhaps it's a distribution. So as I said, you want to perform this analytic continuation from Euclidean to Minkowski. But in practice, what does it mean to perform analytic continuation? You can just follow your nose and do analytic continuation as we are used to doing it, which is you take your Minkowski point C and you connect it by some curve, by a continuous curve, which has to lie inside the forward tube to some Euclidean point. It doesn't matter to which Euclidean point, just pick your favorite point, as long as it's ordered in Euclidean time, tau 1, tau 2, tau 3, tau 4. It can have the same special vectors, x1, x2, x3, x4. It can have other special vectors, doesn't matter, because the analytic continuation, as we proved it, it doesn't depend on the choice of this curve. Pick any curve you like. And once you have this curve, you can now analytically continue the functions z and z bar. So in the Euclidean, you know what z and z bar are. So you can continue, you can compute z and z bar all the way the curve, all along the curve, and see which values they are going to take at the end point. That's what you are supposed to do. So that's very easy to do. So you actually know on general grounds that at the end point, z and z bar are going to be either real, so in Minkowski space, or complex conjugate. But in the process of this analytic continuation, they might, and they generically do, acquire phases. And the values of these phases are going to depend on the causal orderings of the points x1, x2, x3, x4 in the Minkowski space. So here I'm just giving you one example of what you might see if you do this exercise. You pick your favorite causal ordering that you would like to study. You pick your favorite curve. Actually, this exercise you can, by Lorentzian invariance and other properties, you just have to pick for each causal ordering, you can pick one representative point which satisfies this causal ordering. So you pick these initial points z of 0 and z bar of 0. These are z and z bar for Euclidean point that you've chosen. And z of 1 and z bar of 1 are final points corresponding to the Minkowski configuration. You see in this example, they are both real. And you follow the curves. And when you follow these curves, you will see what I'm going to see. First of all, as we have proven, the curves, they cannot intersect. You will never see curves which will intersect this cut from 1 to infinity. Because we have proven that inside the forward tube, rho bar is less than 1, which means that z and z bar never touch this cut. They can only touch the cut at the end point. So if you do this exercise, you will never see the curves touching the cut. And actually, we did this exercise just to make sure, and for many, many random configurations, and you never see it touching. So everything works as it should. But you see these phases, of course, and the phases are important because the phases that z and z bar acquire, they're the same phases as rho and rho bar are going to acquire. And rho and rho bar enter into the final formula for the 4-point function. So if you want to compute the 4-point function, you have to pay attention to these phases. That's like an obvious thing. But what I want to say is that in this particular example that I here consider, z and z bar at the final point are both away from the cut, from 1 infinity. Actually, I'm going to call this cut S channel cut. Right, this is going to be S channel cut. And what does this mean? It means that we are in a favorable situation. So in this case, rho and rho bar are going to be less than 1, strictly less than 1 at the final point. So it means that in this particular case, the Weidmann function is actually going to be not just a distribution, but it's going to be an honest real analytic function for this particular causal ordering. And for many, many, many causal orderings, this is what you're going to see. So I'm going to give some classification results later. Everyone's comfortable with this example? But you might sometimes, and you do sometimes, see something different. You see that you take a analytic continuation, you do these curves, you see the curve circular at the origin, and then, for example, you might see that z bar goes to some value between 0 and 1, but actually z goes to some value larger than 1. So z at z of 1 in Minkowski space turns out to belong to the cut. And then we can only claim, using our results and using S-channel conformal block expansion, that the Weidmann function at such a configuration is a distribution. Everyone's comfortable with this claim?
And what if you use a different channel expansion? Can you then show it's not a distribution?
Excellent question. That is what I was going to discuss next.
Okay, thanks.
Any other questions? So that's what I wanted to discuss next. As Xiang has correctly pointed out, so I was careful. We can claim using S-channel that this is a distribution, but perhaps you can, at this stage, you can say, okay, but let me see, perhaps I can try to learn more using other channels, using crossing and using other channels. Because there is this S channel cut from 1 to infinity. And if you do the transformation to the T channel, which maps Z to 1 minus Z, so you get this T channel cut or you get a U channel cut from 0 to 1. So perhaps S channel cut doesn't give you, it tells you it's a distribution, but it's not a contradiction. Maybe it's actually a function and we might be able to show it using the other channel. Sometimes this happens, but you have to be a bit careful. So when is this going to happen? So let me give you some examples rather than just telling you the general theorem.
Can I ask a question again?
Sure.
Since we're trying to be practical, so let me be slightly practical. If I don't get on the cut, I just start slightly away from it. Once you finite distance away, it is an analytic function there, isn't it?
Yeah, it is.
So the statement of distribution is just in the sense of a limit. Okay.
But if you are away from the cut, you are not yet in Minkowski space. So
well,
you can either choose. You can either work in Minkowski space and then you are a distribution, or you can say, well, I'm going to stay a little bit away from Minkowski space. And then you are an analytic function, which, however, is going might be large, because it's you only know that this function satisfies some power law growth as you approach the Minkowski space. So it's a sort of regulator, yeah.
Okay.
Any other questions?
Sorry, Slava, is it easy to just draw that configuration in a real coordinate space for the 4 points? What does it look like when the Z is going to in between the thing and Z is going to the cut? The one
well,
you had
I actually don't know which plots, I just drew some plots. I'm not sure which configuration they're corresponding to, but I will give in a second some plots which will correspond to actual configurations.
I meant the previous one that you had.
Yeah, I don't know. I just cooked it up, but I'm sure there is some configuration which has this plot.
Okay.
Yeah, in a second, I will give an actual configuration.
Okay, thanks.
So let me give you an example where T channel tells you that we are in business. So the T channel cut is, as I said, so the T channel cut is here. And suppose you have some configuration such that if you drew the Z and bar curves, you see that they go both Z and Z bar, they go to this S channel cut. So they both end up on the S channel cut, but they do it in such a nice way that they never cross the T channel cut, like here, like in this figure. Well, then actually there's no problem. You say T channel cut has not been crossed. So I know using the T channel OP, which converges for its configuration, that actually the Whiteman function is, I've been too conservative using S channel. S channel only tells me that it's a distribution, but in fact, using T channel, I see that it's a nice analytic function. It's no contradiction, and such things happen. So that's one possibility when this can happen. There are actually some more sophisticated possibilities which may happen. Is that sometimes you might see the following thing. You might see that Z and Z bar curves do cross the T channel cut, like here. But these crossings happen in such a way that if you count the total number of crossings up to the sign, then it's 0. Like here, for example, you see that Z bar crosses once and Z count crosses -1 because it crosses from the other direction. So this means the total number of crossings is 0. In this case, you can still argue that Whiteman function is analytic. And the reason is that you can actually modify these curves by adding some loops. which go around the origin so that you can eliminate these crossings without modifying the 4-point function. So there's a little bit of an argument, but it's not complicated. So it's and it's actually what I'm presenting here is well known to the practitioners of this Lorentzian CFT.
This is where you use integer spin, right? Z bar is.
Yeah. So in this case, thank you, Joao. So in this case, I use this condition that h minus h bar was an integer. Is used for this argument. Any questions?
Yes, Slava. So is there any analogous statement about the signed S-channel crossings, or like why is T-channel is preferred here? Like, why do you have a theorem specifically mentioning about the crossing in signed crossing in the T-channel?
Well, you have, so for recall that S-channel is special because for the S-channel, you'll never see any crossings.
I see.
While in T-channel and U-channel, you sometimes have crossings, sometimes you don't have crossings.
Okay, I see. Okay.
And if you do have crossings, then you will only use the channel. You will only allow to use this channel if the number of crossings is 0, total number counted with a sign.
Okay, I see.
So there is an analogous property like this also for the U-channel.
Okay.
And so you see, we have at this point this.
I have a question.
Yeah, sure.
Yeah. So in these last two examples, you have both Z and Z bar ending up on the S channel cut. Is this important for what you were saying, or is it just because the drawing you had before these two, only one of them ended up on the S channel cut?
No, it's not important. Sorry, it was just a coincidence. If for example, one of them ends up on a not on the cut, but somewhere between 0 and 1, then you still cannot use the S channel to show that the function is analytic, but you can appeal to the T channel that it is.
Okay, thank you.
And so, okay, the reason why I present this example is that you realize at this point that there is an interesting classification problem, which you can now do the following exercise. And this was reported by Jashin last year at the Bootstrap conference, is that you can just go through all possible causal orderings. And there is a gazillion of them. Well, not a gazillion, but there's actually 167 causal orderings, which are classified according to different types, depending on which point is in the future of which point. There are these points A, B, C, D, and for each of them, you can put X1, X2, X3, and X4 in all permutations. And this classification, of course, excludes that light cones. We only consider points which are space-like or time-like separated. And for each of these causal orderings, you can see whether there is at least one channel, S, T, and U, which allows you to show that the 4-point function is analytic. And what you find is that out of these 167 causal orderings, there are actually 42 causal orderings without a convergent channel. So almost a quarter of all orderings, well, more than a quarter, using these tricks, you cannot actually conclude that the function is a function, that the Weitman function is a function. So you can only appeal to the theorem that I explained that it's a distribution. And okay, I just want to give you an example of, since also Raghu asked, so here is a particular example of a causal ordering where X3 is in the past of X1, in the past of X4, in the past of X2. That you order points in such a perverted way, and you compute the curves, Z and Z bar curves, then you find that S channel doesn't converge because both points are on the cut, and T channel doesn't converge because the number of crossings is non-zero, and U channel also doesn't converge because the number of crossings is not zero. So you cannot say anything apart from the fact it's a distribution. And there are many causal orderings like
Slava, this ordering, this classification is in Minkowski space, right? So I suppose you get more if you go to the cylinder, to the Minkowski cylinder.
Yeah, you could. So Jashin only did it for.
My comment is that I think in the Minkowski cylinder, the result will be the same because in terms of these graphs, the cost orderings, the total number of cost orderings are totally the same.
But don't you have differences if you cross several light cones? It's not just.
But they're still the same cost ordering, and since they are connected, so they don't. I think.
I mean, usually you get extra phases every time you cross the light cone of the same point, because on the cylinder you can cross it infinitely many times.
I think in these cases the in the Z and Z bar picture, you can see they go around 0 for many times, but I think since this the 2 points with the same cost orderings are connected to each other, so if you continuously go from one configuration to another configuration with the same cost ordering, I think the crossing number will not change. Doesn't change.
Let's say this has not been published, so maybe Jashin, you are correct, but this was not, I think, in your paper. So
yeah.
Okay.
So I cautiously would say that something like that can definitely be accomplished also on the Lorentzian cylinder, but this has not been published yet. But so, however, I would like to state this as an open problem, that this argument that I just described, it definitely does not exhaust the full region of analyticity of the 4-point function, of Weidmann function in particular, because we just use, of course, if the S channel converges, then the Weidmann function is analytic. If T channel converges analytic, use analytic. But we have seen, well, we have not seen, but I already mentioned in the last lecture that in these functions of multiple complex variables, there is this notion of envelope of holomorphy, which sometimes allows you to continue these functions outside of the range of convergence of their power series, just because there are several expansions and you can somehow for free continue to the larger region. And so this needs to be systematically explored. So it's certain that that in many of these configurations where by the simple arguments we can only say that it's a distribution, in fact you can do better and show that it's still a function there, but this has not been done. It's an interesting open problem.
Can I ask one thing? So do all of these statements also apply to generalized free fields, or do you need finite n, or?
Well, generalized free fields, for generalized free fields, you can say much more, because there the 4-point function is just, again, an explicit formula, and there it's a true function everywhere except on the light, for the light cones.
But then you can have bulk point limits and stuff like that, but I guess maybe in that limit one of the channels converge or something.
I'm not discussing here the Lorentzian cylinder. I'm not sure what you're referring to, but I think for the generalized free field, this problem is a little bit trivial. I mean, the problem of classification of analytic domains of analyticity is trivial.
Okay.
What is less trivial is how to convince yourself that the Weidmann function is a distribution. So for this, you have to go through the power law bounds and so on.
Yeah, I guess I was thinking like holographic CFTs too, but yeah.
But you meant also perturbations then the problem changes and the problem becomes more complicated.
Yeah.
So I'm
It's
almost done.
Slava,
Yeah.
maybe I didn't understand the odd number of crossings very well, but it seems here that the number of U channel crossings is odd in this figure that you drew here. So couldn't I use the U channel in this figure?
Yeah, it's odd, but what it needs to be zero. So for example, in this example, I had one crossing here and -1 crossing here because it was from the opposite direction.
Oh, I see. I see.
So if only one curve crosses, then it's like that. Then you cannot do the trick.
Okay, okay. The condition was that the total crossing has to be 0.
Yeah, and here I have like both -1, -1, so it doesn't work either. So here.
I see. Okay, thanks.
Yeah. So I'm a bit over time, but I'm almost done. I just want to discuss one more thing and a couple of open problems, because I was discussing this thing about crossings and how sometimes you can undo the crossings by adding the loops. But this connects to something that was discussed also yesterday, mentioned in Madalena's talk, is that this should remind you of this situation, which is the light cone limit on the second sheet. So let me remind you that in this light cone limit on the second sheet, you perform the following operation. You take your, so here it's not necessarily, I mean, usually it's in connection with Lorentzian physics, but we can describe it just in terms of Z and Z bar. What you do is that you take your function, 4-point function of Z and Z bar, and you analytically continue just Z through the T channel cut. Well, you don't analytically continue Z bar. And for example, you might want to do it in such a way that neither Z nor Z bar touch, for example, S channel cut. So for example, here, S channel cut is not really a concern. So I didn't touch the S channel cut. So you know that the 4-point function is analytic, because using S channel, you know that the 4-point function is analytic. But what we would often would like to do is to get some estimates, to get some asymptotic, some understanding of the asymptotic behavior of the 4-point function near this point, because Z becomes very close to 1. And so it's very tempting in such a situation to say that if Z is close to 1, then perhaps we can somehow use the T channel to infer asymptotics near this point. And well, it's very tempting, but it's, you know, it's not really legitimate, because the T channel is not convergent, because we only continued Z through this cut, but not Z bar. And so in fact, you know, everyone agrees that the T channel is not convergent, and so people say that perhaps the T channel is not convergent, but in some asymptotic sense. Maybe if you just look at the first few terms in the twist expansion, then maybe you can still trust the T channel and so on. And well, perhaps, but this has never been shown. So I would like to emphasize two things. So first of all, in our work on this Lorentzian CFT, we never had to appeal to the light cone limit. So we were actually able to show that everything was under control without appealing to the light cone limit. So you can do actually many things without appealing to the light cone limit on the second sheet. But there are some important arguments that are really hinge on this T channel on the second sheet asymptotic. And for example, it's used in the Anik proof. And it's also used, as was reminded to us yesterday by Madalena, if you work with the Lorentzian inversion formula, and if you want to show that it defines to you an analytic function of delta and J, then you have to integrate over the diamond, And so in order to show that the function is analytic, you have to show that the integral converges. But what you are integrating is this double discontinuity, which involves this analytic continuation to the second sheet. And so you actually need to know this asymptotic even to show that what you get is an analytic function. So unless you have some argument, you don't know that the function is analytic. So it's
Sorry, Slava, the light cone limit on the first sheet would be just Z going to 1 directly without crossing the cut.
yeah, that's according to this terminology, and that would be perfectly fine because it's convergent.
Okay, so the problem here is you cross this T channel cut and then went to Z equal to 1.
Yeah, that's the problem. And so I would like to formulate this as an important open problem, in my opinion, is to prove this light cone limit on the second sheet for asymptotics. Because this is really, in my opinion, it's an important missing step in these proofs and in these arguments. And as the community, we have to, it's understandable that the people who first give these arguments and first give these proofs, then they have a poetic license to maybe dream that certain steps are there and they will be completed, but the steps need to be completed, and the Ionic proof is already 5-6 years old, and this has not been completed. So either we should recognize it as a gap in the proof or we should complete it. So
sorry, just a question.
Yeah.
So that's this thing you're asking for is roughly equivalent to the light cone bootstrap for the anomalous dimensions having a unique solution. I'm not sure if it's exactly equivalent or just roughly equivalent, but do you have any comment on that?
I'm not sure, Tom. I looked at your argument in your paper, and I'm not sure I can complete it in a watertight in a watertight argument. That indeed there are some similarities of spirit that indeed they recognize some merit to your intuition, but I think what we are asking here is more than that, because
yeah, I don't know if there's a rigorous statement along those lines. That's what I was wondering, I guess.
Yeah. So I don't know. I think that this T-channel expansion might have a much larger region of convergence than we naively infer from the OPE, because of all this envelope of holomorphicity and whatnot. So it might be that there is actually some miraculous, robust argument that will show that all this is correct, and otherwise, yeah, we should accept it as an axiom. It sounds a bit strange because it's not a very robust statement. So we have to think a little bit about it. And my hope here is that there are many young, bright people looking for interesting problems, and so this maybe someone will be motivated to think about this and come up with a different argument, or maybe complete your arguments, because you indicate some lines for attack on this problem, and maybe somebody should look into this more carefully.
Okay, thanks.
Sorry, I have a related question about this. So for the conformal Regge theory, we could work out the asymptotic behavior of a correlator in the Regge limit, which is a bit similar to this configuration. We also send Z around the T-channel cut. The difference is that we send both Z and Z bar to 1. So there we can work out the asymptotic behavior by appealing to the Sommerfeld-Watson transform. And there, using this analytic in spin and dimension both, well, assuming this is spin high. So let me say it's involved logic between analysis in spin assumption and actually using the sum of Watson. But what they do in the conformal Regge theory is that we continue the spin to some negative or small real number, and then for the imaginary part, it can be anything. That's how they avoid this divergence of T-channel expansion and to work out the Regge behavior. But can't we do that similar thing for the second sheet icon limit?
Well, I mean, I wish somebody, what I'm advocating here, and I was going to give a list on my conclusions page, is that I think everybody, I haven't yet seen in our community someone who would say that Lorentzian CFT needs some extra assumptions. It seems like everyone is happy to say that Euclidean axioms are so nice that everything should somehow follow from them magically. What I have presented here is just some like modest first step how to demonstrate some aspects of Lorentzian CFT physics from Euclidean CFT, and hopefully, without jumping any logical steps. So this conformal Regge theory, I think, is on the to-do list, because what are we going to do about this analyticity of C delta J? So we have to, I think, first put also Lorentzian inversion formula on a bit more solid grounds, and then perhaps one day we will put also conformal Regge theory on a similarly solid ground. I mean, if we manage to reduce everything to Euclidean CFT, it's going to be amazing. If not, it's okay, of course, to use other assumptions. I don't, we shouldn't forbid ourselves to use various assumptions as long as we think that there are some classes of theories which satisfy these assumptions. I'm sure there are many theories which satisfy those assumptions that people use in conformal Regge theory. What I wish that people would say, yeah, well, we're using these assumptions or those assumptions, and state somewhere clearly, so that when like 5-10 years down the road, we still have kind of literature in order. Mathematicians derive theorems assuming Riemann hypothesis, and it's not considered to be a bad thing to do. But you just write, well, assuming Riemann hypothesis, something follows. Assuming Regge theory, something follows. Let's just do that.
Yes, thanks.
So let me just give you this list of things that we haven't done. I talked about Whiteman functions, but one should also revisit time-ordered correlators in Minkowski space. So these are also supposed to be distributions, but you cannot just recover those distributions from Whiteman functions, because then you will need to multiply Whiteman functions by some theta functions, and that's just not a valid operation in general. So you just have to analyze them separately and see what happens. But this should be doable. There are other interesting properties in Lorentzian physics, which is, for example, there's something which is called wedge reflection positivity. I'm not sure what the status of this is. It doesn't quite follow from Whiteman axioms. It usually follows from Kastler axioms, which I did not discuss at all. But perhaps in the CFT we're in better shape and we will be able to derive them, and maybe even in some distributional sense. It will be nice to figure this out. I don't know. So there are some things about higher point functions that we haven't done, for reasons that I may explain if people ask. Then some things that we haven't done, but it's upcoming. It's about non-scalar operators and Lorentzian cylinder physics, that those things can be done rather easily. And I also mentioned this envelope of holomorphy and light cone limit on the second sheet. So I encourage people to think about all these things. Thank you.
Thank you very much, Slava, for this very nice set of lectures. More questions?
I just have a couple of clarificational questions. So in this Cauchy-Schwarz inequality for R of C, is the right-hand side with the square root less than 1? Did you say that actually, or did I miss?
It is because it is less than 1 because, as I said, these terms
Or less than 1?
are less than 1, which is easy to verify by an explicit computation.
Okay.
Because it's a 2D, it's like a 2D CFT calculation of error bar.
And the other one I had was that in the first example that you gave of the path of analytic continuation, you said the function is real analytic. And I know you answered to Joao the other day about the meaning of real analytic, but could you say one more time what the definition of real analytic is?
Yeah, so real analytic, so you have a function f, which is a function from Rn to complex numbers, is called real analytic if it is analytic in some, if it is analytic in some small open set containing Rn. So where U, it has to be an open subset of Cn.
I see.
Which can be arbitrarily small. So it basically says that function is analytic if around every point, it's a function defined on Euclidean space, on real Euclidean space, and around each point, it has a convergent power series. But the radius of convergence of this power series can be arbitrarily small. It can be x-dependent, arbitrarily small.
I see. So as you move around in Rn,
yeah,
the radius of convergence might get very, 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 very small.
Yeah. The point is that you cannot say mathematically the function on Rn is analytic. You can only say that the function is analytic if it's defined on an open subset of Cn.
Right. Okay, thanks.
But notice, so as I was saying, is that real is referring here. It's not, it has nothing to do with where the function is taking its values. It can take a value in R, in C, in some vector space, in some Banach space, and so on. As long as it's defined on Rn, we should call it real analytic.
The point is the U may not be open in Cn, right? That is the point that, or
no, okay, U has to be open in this definition. So you have this Rn, and you can find some sort of small neighborhood of Rn where the function is analytic in the usual sense.
Okay.
Does it make sense?
So
I mean,
we will also say,
think about 1D situation. Suppose that we just had C as one-dimensional case. Can you say, look, would you be okay with saying that the function f of x is analytic if it's only defined on the real axis? Would you say that it's analytic?
No.
Yeah, so mathematicians, if they have a function which is only defined for real x, then mathematicians don't call such a function analytic. If it's defined on some subset which is open, or it has been extended to such a subset, then you say, yeah, it's analytic on this subset.
Okay, thanks.
I have another question which is perhaps related. So we know, or we expect, that there are some singularities once you start continuing the 4-point function, which are not light cone related. So Well, in your picture, I guess it would be when, for example, when z becomes equal to z bar after going around some of the cuts. So I think, wouldn't that already tell you that in your strong sense that for some causal ordering, you want to say that the Whiteman function is like fully analytic? We don't expect that. We expect it to have some singularity inside one of these causal diamonds, if you want.
Yeah, that's true. That's what we expect. We expect that it's probably too much to ask that the Whiteman function should be analytic everywhere except for the light cones.
Right, that I think is too much to ask, but there should be some kind of middle ground that it's still a function, but it will have some singularities, which we can understand in terms of some Landau singularities or something, because, yeah, I think it's basically Landau singularities. Like
So are you saying that some of these causal orderings, so there are some causal orderings, and you're saying that some of them may harbor these Landau singularities?
Yeah.
And the best we can hope for is to prove that the function is analytic everywhere away from these Landau singularities.
Yes, that
Yeah.
I think would be my natural guess, my optimistic
Yeah,
guess.
I think Peter made already some steps towards this result. So he managed to show in some cases that I think he managed to extend the 4-point function even beyond some of the regions that Jashin has found, and but not all the way to the Landau singularities, of course. Using some of this envelope of holomorphic tricks, but I don't think he has a full solution of this problem.
A naive question: did Landau singularities persist non-perturbatively, or is there?
So Landau singularities, you can view it like this. I think you can write down some conformal integral which has this singularity somewhere. And so you would expect that if you are just using conformal invariance and analyticity, then since this conformal integral is analytic and conformally invariant, then probably by very general arguments based on conformariance analyticity, you shouldn't be able to rule out those conformal integrals. So you should probably expect that with this approach, you will not be able to show that there is no singularity there. Now, in a real CFT, I'm not sure what do people believe. Should there be a singularity in a real CFT, or should it be somehow smeared? I don't know.
I think there should be. I mean, there is this really physical picture of particles propagating and interact. I mean, I think this is the best explanation. This is the bulk point limit point. So you can read if you get convinced. But
for example, in 2D, we know that there are no these bulk point singularities, right? In two-dimensional CFTs, we know that you can actually analytically continue the 4-point function, and it's analytic everywhere except on the light cones.
Yeah, but there is also no Landau singularity. So
there's also no Landau singularity. Okay, thanks. So there is no contradiction.
But these bulk points, they demand the local bulk theory, right? Which you would not have at finite n. So they things. I mean, in the theory of quantum gravity, they appear in the large C limit.
Yeah, so sorry, Walt, I was not being precise, right? So there are Landau diagrams in the bulk and Landau diagrams in the boundary. So you are right that bulk point singularities should not really be present here in the non-perturbative CFT, but there are still Landau singularities just in the boundary theory. So some of these will still survive. Yeah,
those cannot be ruled out. Yeah.
I had a related question. What's known in terms of examples for distributions away from the light cone are there any CFTs where we know this happens?
No.
No. And in terms of singularities away from the light cone, apart from these Landau singularities, do we know other examples?
So sorry, I was thinking about examples, so I missed the second question, because I thought that, you see, in principle, you could say, in principle, you could try to study this empirically. You could, like, for example, take three-dimensional Ising model. So we know a lot about the Euclidean four-point function in the three-dimensional Ising model. And you could say that I told you that, you know, in Euclidean four-point function, you can construct the Weidmann function everywhere. So perhaps by doing this, you could hope to see if actually somewhere there is any sign for this distributional nature. You can try to do this, because also we show in our paper that the conformal block decomposition converges in the sense of distributions in Minkowski space. So for example, take a conformal block. Conformal block is an analytic function away from the light cones. I think that's a correct statement.
Not quite, I think, Slava. I think if you continue, for example, in 4D, you have 1 over z minus z bar pool.
1 over z minus z bar. But apart from this z minus z bar, z minus z bar, if you just continue.
Then yes, I think so, yeah. It's
yeah.
hypergeometric, you just continue. Yeah.
So the conformal block is a distribution, but actually it's a function, and it's a better as a function. It's apart from this 1 over z minus z bar, it's basically a function in Minkowski space. So you could actually consider this conformal block expression in Minkowski space and see if it converges to a function or a distribution for all possible causal orderings, and see what happens. The problem is that we only, it turns out that this conformal block space converges very slowly. So unlike in Euclidean space, where we know it converges exponentially fast, if you are deep in Euclidean space, we can show that it converges in Minkowski space only as a power. So I'm not sure what you will find if you apply this whole machinery to 3D Ising, but maybe this can be tried. If somebody is interested, they should try this.
Mm-hmm.
But your second question was, what was the second question, Silvia?
Oh, it was just about the singularities instead of distributions away from the light cone. I mean,
like, for example, take these conformal integrals that I was saying exist and see what kind of singularities they have and what is known about them.
I guess that's probably a hard question.
No, I'm sure it's there was actually some work after Jashin's paper. There was a paper by some people from Berlin who actually like analyzed some conformal integrals and saw some singularities.
Mm-hmm.
I forgot what were the name of the authors, but I think they have some explicit examples of this conformal integral where you could see some singularities, and they found some interesting parallels with what Jashin was finding. So I guess some data is there, but I haven't studied it.
Mm-hmm. Okay, thank you.
Hi, Slava. I have a question about higher point functions, because so on the one hand, it looks to me like the cross ratio space approach is going to be vastly more complicated, right? If you have a 5-point function, I mean, you'll have to think about analytically continuing in several cross ratios. Now, I think what you show is the convergence of the OP as distribution also applies to the Fourier transform Weidmann function, right? So would it be a good way, you think, to proceed through this momentum space approach for a proof for higher point function? because they're really like the OPE factorizes, right? So for a 5-point function is like two OPE for 4-point functions. Did you see what I'm saying? Or is there, do you have a strategy to attack those?
I roughly see what you're saying. So you could, so what I think what you are saying is that you could somehow, so this Whiteman function that we know, it has a Fourier transform, and the Fourier transform is a distribution. So if you could somehow, and as in our paper, we have shown that the conformal block expansion converges in the sense of distribution. So we can now Fourier transform term by term. Actually, the Whiteman function has a satisfied spectral condition, has Fourier transform in the forward light cones. Each conformal block on the boundary also satisfies the spectral condition. So couldn't you somehow just, for example, if you knew that this conformal block expansion, if you knew the Fourier transform of conformal blocks explicitly, couldn't you just somehow prove that it converges in the sense of distributions? And that would give you the distribution, the Fourier transform of the full Whiteman function.
Right.
I don't know.
Because it looks like there you could.
The way we did it, and I'm not sure how feasible it is.
Well, I don't know how feasible this is, but somehow for the 4-point function, now this is more or less established, no, in some sense. I mean, the convergence, you established the convergence in a different way, right?
But now you would like to reverse the logic, right? You would like to somehow bypass our argument, hoping that everything could be simplified by using the Fourier transform. That I don't see.
I'm not sure that this is possible, but I would buy your argument for the 4-point function to show to argue that for a 4-point function the Fourier transform of the blocks is gonna give you something convergent, and then I would like to iterate this to go to 5 and higher point functions.
Well, this iteration step, I don't have. I don't know how to make it work. Actually, there are several reasons why we didn't do higher point functions, and I think the necessity to work with several cross ratios was not the main reason. In fact, we don't even have, I mean, laugh if you wish, we don't have a good system of axioms, say, for 5-point functions.
No.
So how is this possible? Because, well, that's kind of a separate discussion in a sense. I don't know if now is the good moment to start it, but basically you need to have some sort of axioms which will tell you that you are allowed to use OPE several times and commute OPE series and so on. And there is just not a natural way to formulate such an axiom. It doesn't seem to be, without appealing directly to the Hilbert space, which is something that we didn't want to do right away.
Okay.
And since we didn't see a natural axiom for 5-point functions, we kind of didn't go in this direction. But someone should think about this. In 2D, the situation is better, but somehow the d larger than 2 generalization of higher point function axiomatics doesn't look natural. But that's a separate discussion. Otherwise, if you have a good axiom, I think if you know that everything converges and you could multiple series converge, I think you could work it out, multiple cross ratios, fine, no problem. It would be interesting to work it out, but I'm sure it could be done.
Okay, thanks.
Well, I don't know if there are other questions, but I would be very interested in hearing a bit more about this problem, Slava, if you could just briefly, or does it take too long to explain?
No, it doesn't take too long. If there's interest, I'm very happy to say a few words. So, the simplest axiom that you can imagine is, and that's the one that we used in our paper as a starting point, is the fact that the OPE converges if there are two operators that you can surround by a sphere which separates them from other operators. That, you know, everyone is happy with this axiom, but you have to be a bit careful when you say, okay, what does it mean that OP converges? So there is an OP series. So there are some, you will get, well, let's suppose that it's 0.0. So there are some x to the alpha terms. So this is the x expansion. And then there is something which, something else, right? So there's some coefficient. So this series, you have to explain, like, how do you sum this series? For example, are you supposed to like take every term in absolute value, or maybe you're supposed to do something else? That's not totally innocuous if you think about it, because you would like to have a definition which is somehow invariant with respect to the change of basis. And if you are just dealing with one point, then one way you can say is that what you're supposed to do is that you take this series, you sum it, for example, over all multi-indices up to n. So now you have a sequence of functions Pn, and you just demand that this sequence of functions Pn converges. That's a very weak form of OP axiom. It's extremely weak because we do not, in this axiom, we do not say anything how the rate of this convergence depends on all the other points you have in your correlation function. For example, let me just move these points a little bit, or maybe move one of these points a little bit. So the fact that the first series converged, it means that you can take n sufficiently large and the area you're making is small. Now, suppose that you moved one point from x to x prime, well, not like a point x3 to x3 prime. So now, again, the OP converges. So there exists a sufficiently large n prime so that the area is small. But how is this n prime going to depend on the shift of x3? You would like to perhaps optimistically say that it shouldn't depend, that somehow you should be able to choose n, which uniformly, which is the same n. If you just shifted the x3 a little bit, then this n should not change a lot. So this kind of this sort of things actually turn out to matter, because what you would like to be able to do is you would like to, we always say that OPE allows you to reduce n-point functions to 3-point functions. But in order to do this, you have to use OPE repeatedly, of course. And so you're going to get a double series. So you're going to get the sum over alpha x to the alpha, and then maybe sum over beta y to the beta times something, or maybe even multiple series. So now you have to explain what it means for this series to converge. For example, are you supposed to like cut off this up to n and then cut off this beta up to m? And what is the choice of this n and m? For example, are you supposed to be able to choose n equal to m and then choose them sufficiently large? Or perhaps you should choose n large and then for every n, choose m, which can be large, but larger and larger depending on n. These sound like stupid technicalities, but actually that doesn't seem to be a very nice natural choice. And since, yeah, I don't personally see it.
So this, if you said they were like absolutely convergent, then
it wouldn't matter. Then it wouldn't matter. If they were absolutely convergent, then it wouldn't matter, because for series with positive terms, then this issue of n and m being unequal, it doesn't play any role.
So why can't we say that if we have that intuition from Hilbert space, right? That it should be absolutely.
Yeah, because if you want to say that the series are absolutely convergent, it turns out that you shouldn't expect expand in X alpha, but you should expand in the orthonormal basis of descendants. So these X alphas, they multiply, okay, when you take O of X, and so this multiplies the alpha O, right, at 0. So it doesn't seem to be natural to put on X alpha absolute value, because X alpha doesn't multiply anything particularly nice. X alpha multiplies P alpha O. What is P alpha O? It's not, for example, different P alphas, they're not even orthogonal, right? We know that P alpha O is not orthogonal to P beta O. So why are we choosing this particular basis P alpha O? It's not a God-given basis.
Sorry, just to understand. So alpha before was an exponent of modulus of X, and now it's is it still
No,
that?
alpha is like a multi-index. It's alpha 1, alpha 2, alpha n in alpha d in the dimensions.
I see. But I thought before it was just a power, like from the power law.
Well, it's a product of powers, x1 to the alpha 1, x2 to the alpha 2, xd to the alpha d.
I thought if you go to your picture, you said, if I can draw a sphere, it converges. So if you use coordinates that you expand around the center of the sphere,
yeah,
then there are angles and radial, you can just expand in the radius, no? Isn't that something like that? Because that's what the Hilbert space would tell you, right? You should expand in radial quantization in the center of the sphere, which you know splits the 2 points from the rest.
So if we write r to the d, so if you write r to the well, not to the d, to the absolute value of alpha, you want to write it like this: r to the absolute value of alpha times some polynomial which is going to depend on angles. This is how you want to write?
Yes, but I think it's important that the r is really centered on this. I mean that you.
Yeah, let's assume that it's centered. That's not the issue. The issue here is that this polynomial, it depends on the choice of the basis in the space of descendants of operator O.
But so I would say that this would be absolutely convergent now, that you could take norm of P, modulus of P, and it would still converge.
No, if you pick a stupid basis in the space of descendants, it's not going to be. Because I can do some linear transformation in the space of basis from some. There is some good basis which is the orthonormalized basis. I can pick descendants on every level which are orthonormalized. That's a good basis. But now let me take some other basis where I transform this orthonormalized basis by some linear transformation with huge coefficients to some very non-orthonormalized basis.
But I'm confused because r to the alpha, there's a finite dimensional space, right, at each modulus of alpha.
It's a finite dimensional space, but on every level I have to pick some basis. This problem did not exist in 2D because there was just z to the h, z bar to the h bar, and since the rotations, there were two rotations, there was a natural basis. Here in higher D, the only natural basis seems to be the one with respect to which the Gram matrix is diagonal. If you pick a wrong basis, it's not going to be absolutely convergent because you can make these coefficients P of theta. Some of them are going to be very large and positive, others are going to be very large and negative. If you pick some perverted basis, then you take absolute value and you're going to screw up convergence.
Yeah.
But it's perverted, right? So this clearly, what you should say perhaps is that we should expand in this orthonormal basis, and then it should be absolutely convergent. But even the orthonormal basis is not unique.
But I'm confused. If you draw the cylinder picture, there will be 2 points below tau equals 0, and all the others will be above tau equals 0.
Yeah.
And so if I insert a complete basis in this tau equals 0 surface, complete base, which is eigenbasis of the Hamiltonian, I just get this r to the alpha times some polynomials. And so isn't this precisely?
So how is this consistent? You are saying how is this problem that I'm pointing out is consistent with Hilbert space convergence?
Yes.
Well, it's consistent because in the Hilbert space, yeah, so it's consistent, first of all, because in the Hilbert space, we are going to say that the state of two operators in, we are going to act on the vacuum. It's, of course, it's going to be approximated by a sum of, by some states, which are, well, it's going to be some limit of states. Where n is the level. I'm going to sum up over all operators, including descendants, up to level n. And this convergence is in the sense of the Hilbert space. This is, we would like to aim towards this statement, but we would not like to assume it as an axiom. So this convergence in the Hilbert space is not the same as the absolute convergence of the OPE. Because the operation of taking absolute value of a coefficient of this X expansion has nothing to do with the Hilbert space unless you pick the basis, which is orthonormal basis in the Hilbert space. Does it?
Sorry, I understand. You should have, yes, P of theta is a sum coming from different orthonormal states, and you should take the sum of the squares and not the square of the sum.
Yeah.
Sorry, yes, I understand now. Yes.
So it looks like either you should somehow formulate a system of axioms which bring in this Hilbert space structure early on, and perhaps that's what we would like to do, what we will have to do, or something else. But we didn't want to do Hilbert space early on in this paper. In fact, interesting thing is that for 4-point functions, if you start from this very weak axiom that I started with at the very beginning, where you just have a convergence of these partial sums, pointwise convergence of the partial sums, it turns out that for 4-point functions, from here you can get to the Hilbert space and you can prove the Hilbert space convergence, which is a priori looks much stronger, but it follows from this axiom.
Thank you, Slava. Thank you for the clarification. Very good.
It's a bit technical, but yeah, I'm not happy. I'm not fully happy with how, with axiomatics for higher point functions. It has not been, I haven't seen natural formulation yet.
Any other questions? Okay, if not, let's end with a big round of applause for the great lectures of Slava. Thank you very much, Slava.